So this is just another one of my concept bite videos, this time on Marcus theory, specifically focusing on the Marcus inverted region. So I'm just going to start off with just kind of a recap, an idea of what this photo-induced electron transfer concept is. Here I have a donor and acceptor system, and I can see from my energy level diagram on the right hand side of this screen that I don't really have enough energy to move my electron from my donor to my acceptor, because my acceptor LUMO is higher in energy than my donor HOMO. I can, however, make the donor have more energy by making it absorb a photon of light. So I bring in a photon and I have an excited state donor, and now I have an electron in an orbital higher in energy than the LUMO on my acceptor. So then I'm able to transfer that electron from this excited state on my donor molecule to this empty LUMO orbital on my acceptor, giving me this charge transfer. This is a really important concept, particularly when we're dealing with photovoltaics, where we're trying to ultimately have a charge separation, a battery, harvesting energy from the sun. So there's other important factors which are going to affect my my rate of electron transfer. And there's something very important which introduces a potential barrier where we potentially think there shouldn't be any. Here I have just a very simple donor and acceptor system, and it's an isoenergetic system. So essentially I'm just shuttling an electron between two identical molecules. As I move my electron between my donor in pink and my acceptor here, it is essentially an instantaneous process. It's much, much faster than the reorganization of the solvent. In other words, it takes time for that system to reorganize itself, to optimize itself for the movement of this electron. Eventually, after a few nanoseconds, it does. But that movement of an electron is instantaneous. It's femtoseconds, potentially picoseconds, but femtoseconds quick, 1,000,000 times faster than the time it takes to reorganize the solvent. We've seen this already in the Franck-Condon principle, and this is just the same thing used here. But the fact that the solvent and the molecules take time to reorganize themselves for the accepting of electron gives us this very interesting property. So here I have just a potential well, two potential wells. The pink is essentially my reactants, and the kind of tealy colour my products. And it's an isoenergetic reaction. There is no difference in energy overall between my reactants and my products. And I have this reaction which has an activation barrier. This activation barrier, which I've called G double dagger, is very, very important. Because even though the reaction itself has no change in energy, it still takes me energy to do the reaction. As I promote an electron vertically, that means that when I excite this system by transferring my electron from my donor to my acceptor, or moving my reactants basically from reactants to products, I'm doing that as a vertical transition. And the overall activation barrier is related to this overall kind of energy of this transition, because it's 1/4 of this value lambda, and lambda is normally referred to as the reorganization energy. So the amount of energy it takes for me to reorganize the molecule to kind of accommodate the difference between the state it excites into and its natural ground state is my potential barrier. As I change my value delta G, I change the height of this activation barrier because I change the amount of energy to reorganize this system. If I take this to an extreme, I can actually get a system where I end up with delta G dagger, my driving force for my reaction, being 0. So here, my third one along, I have a system where the driving force for my reaction and the reorganization energy are the same magnitude. And you can see now that I have no potential barrier, no G double dagger. And so my reaction here goes as fast as it can possibly ever get. As I increase the driving force still further, I can see that I introduce that energy barrier to moving my electron again. I see this step that I have to get to go from the bottom of one well up over that potential barrier into the other well. This concept that I can slow down the kinetics of a reaction by increasing the driving force is massively, massively important. So just one other note, what do we mean by this reaction coordinate? Well, essentially it's the difference between the structure of the donor, or of the reactant rather, and the product systems. The bigger the structural difference, the bigger the offset of these two potential wells. And as we can see, the bigger the potential barrier that I introduce. So the slower the reaction. So reactions which have very, very similar structures of reactants and products have very small changes in reaction coordinates. The two potential wells overlap a huge amount, and I have a small barrier for the activation of that reaction, a small potential barrier to overcome. So Marcus' theory links kinetics and thermodynamics. It links this idea of this traditional kind of classical activation barrier to the energy required to overcome that transition state energy, which links to exactly how much energy it takes to reorganize once I move my electron from my reactant to my product. When I have a particular size barrier, when the size of the driving force of the reaction and the size of this reorganization energy are the same, then my kinetics reaches a maximum rate because there is essentially no activation barrier for the kinetics to occur. But if I increase the driving force beyond this, I slow it down because I reintroduce this activation barrier. Why does it matter in terms of photochemistry? Well, it matters because by the time we start injecting photons into systems, we're giving systems lots of energy. And so it can be a problem that we actually start to slow the kinetics of our reaction down by trying to make the system more favourable. Hope this has been helpful. I'll be back with more.